So, good morning, everyone, and welcome to this first session on the doctoral meetings. Sorry, there's a mistake here. In this track, we're going to be hearing about 4 PhD students working on computational and experimental aerodynamics. And they are Jungwei Chen, who will be talking about his thesis on data-driven flow measurements. Exan Frasanmik, who will be talking about statistical learning tools for turbulent flow control. Jacopo Tirelli, who will be talking about his thesis on data-driven enhancement of optical measurement techniques. So 3 theses on experimental fluid dynamics, mixing data-driven techniques, and trying to characterize flows. So very interesting talks. And then Juanma Catalán, who will be talking about his thesis on unsteady aerodynamics of flapping wing micro air vehicles. This is a more numerical aerodynamics thesis. So thanks very much for being here. And now.
Okay, so thank you for having me. Thank you all for attending. Today I'm going to present my doctoral thesis progress through this presentation, which I've called The Unsteady Nature of Micro Air Vehicles Aerodynamics, the Effect of Free Stream Perturbations and Uncertainty, okay? So first of all, why are we interested in here in this, right? Basically because micro air vehicles, well, are increasingly more demanding for several applications, security services, protection, surveillance, etc. The thing is that they usually operate in gusty environments, in the atmospheric boundary layer or urban environments or whatever, where they usually are subjected to velocity perturbations, which are usually of the same order of magnitude of their size and velocity. So, what are we really interested in here? Basically, we are interested in the aerodynamic response of these vehicles under perturbation, what happens in these gassy environments, and so on. And this is why we have addressed this study in 2 different branches. Okay, first one is performing direct numerical simulations of flows around bodies of interest, which are subjected to inflow turbulent perturbations. Okay, this is a problem, a 3-dimensional problem that is computationally expensive. Okay, this is a detailed study. Okay. Another thing we have addressed is to perform uncertainty quantification analysis using low-order aerodynamic models and cheaper computational simulations to see how some stochastic inputs affect our responses, okay? I'm gonna first address the first part and later I will talk about uncertainty, okay? So, well, talking just a little bit about free stream perturbations, which in the literature is usually called synthetic turbulence inflow generator. Okay, from now on, STIG. As you see in this scheme, okay, we usually have an external aerodynamics problem where we can have an airfoil or another body of interest, and we usually have a velocity coming from an inlet. And we want to study the effect of this flow around the body. Okay. If we want to study the effect of perturbation on this body, a solution would be to impose this perturbation from the inlet as a boundary condition. Okay. The thing with this approach is that usually the grid size on the inlet is the cell size, let's say, is much coarser in this region, so that this coarseness, let's say, usually give rise to the impossibility of resolving small flow structures, and then we also end up having hardly avoidable damping effects due to the numerical scheme. Okay, so. What we are addressing in this thesis, among other things, is to generate this perturbation not on the inlet, but on a region that is much closer to the body of interest. Okay, as you see in the scheme, we are generating the perturbations somewhere upstream of our airfoil or our body. Okay, basically, I'm going to explain to you now how we do this. Okay, so. Basically, in order to solve our our problem, okay, we are solving our incompressible Navier-Stokes equations with our in-house solver Toucan, okay. This solver uses the immersed boundary method proposed by Ullmann, uses a fractional step method and a Runge-Kutta of 3 stages, okay. So basically, you see here the equation, the typical equations, but with the difference that we are adding at the end of the equation, we are adding an additional source term, which is called f stig, okay? This f stig is gonna be the source term that is going to introduce these perturbations, okay? And you see the shape on the right hand side of the slide, okay? This equation comes from it was proposed by Schmidt and Breuer on his paper, okay. And the thing with this, the thing why we want to introduce this sort of in this way is because we want control over the integral length scale of our perturbations, and thus the time scale by using Taylor hypothesis with our free stream velocity. And also we want control over our turbulent intensity, okay? And since we want control over all this, we are gonna use the concept of digital filters, which was first proposed by Klein in 2003, okay, in his paper, which is actually a very famous paper in this topic. In this slide, I'm addressing how we do this. I'm not going to enter much into the detail, okay? But the thing is that we have our source term that you see in the upper part of the slide, okay? And in the end, we want to compute the U prime, which are our perturbations, okay? The rest part of the source term, I'm going to explain it a little later. But by digital filtering, we basically compute this U prime, okay? So the thing here is that we need to generate an inflow, a two-dimensional inflow, which will correspond with this region. Okay, in here we want to generate a two-dimensional inflow in the whole plane, in this case YZ, and we do this by starting with three-dimensional blocks that we want to filter 3 times. Okay, first in X, then in Y, and then in Z. Okay. And this approach of 3 one-dimensional filters was proposed by Kempf, which is sort of improvement of what proposed Klein in his paper. Once we have this, however, we need to define our filter coefficients, okay? This time Bx, By, and Bz, okay? So we compute our filter coefficients by imposing a Gaussian autocorrelation function, okay? In this case, which provides us, or better said, allows us to create 2-point correlations in our perturbations, okay? This is something we want, actually. Once we impose that, it can be demonstrated that the filter coefficient can be simply computed as we have in these equations. This was proposed by Klein, again. And that the filter width is also demonstrated that is twice the number of points we need per length scale, okay? Finally, we introduce new randomness at each time step in these 3-dimensional blocks so that the time scale is preserved, okay? So finally, we end up having an integral, thanks to this autocorrelation function, we end up having an integral length scale, that is our input scale that we want. So we have control over this, and we have also homogeneous and isotropic turbulence, okay? Once we have this U prime computed, okay, we want, which actually will correspond to this coordinate xc of this region, okay? We want to spread this xc over this 3-dimensional region, okay? We're gonna do this, or influence region, as I call it in here. We're gonna do this by imposing a Gaussian bell shape, okay, this shape, so that we have the data that we have generated, we have here full, and then we are gonna spread it between xc minus L and plus L, so that we end up reaching a whole influence region with our perturbation being generated step by step. Okay, also this will be the Gaussian, okay, in the source term, actually, what I've been talking about in this slide, this whole Gaussian, and also we divide by the time scale to preserve the autocorrelation as it is introduced in Schmidt and Breuer paper, okay? So in here, I'm showing some intermediate results of DST, okay? These are three-dimensional simulations.
Oops, I think he's gone. Palma?
But you didn't were able to hear me. So in here, I'm presenting some intermediate results, okay, with the flow of a cylinder subjected to turbulent perturbations with length scale 0.2 quarts and turbulence intensity 15%, okay? As I was introducing, basically you see here that we are generating these inflow perturbations, okay, just slightly upstream the cylinder, where the grid, as I introduced before, is finer. Well, in this case, it is not finer because I'm using a regular grid, okay, with constant spacing. But the idea of this method is to introduce this perturbation where the grid is finer, okay. So we will do that in further simulations. So the idea is that the perturbation interact with both the cylinder and the wake and the von Karman street, as you see in the video, and then here we have what would be a snapshot of what is happening in this influence region, okay, in the middle actually, as I presented before. This is actually what is being generated with the whole influence region at each time step, okay, and this has, so this interval length scale 0.2 and a turbulence intensity which is measured in this color, okay. So we also have this time signal, which is simply let's say a time series of a point in the inflow plane, and you see that the signal is actually, I'm plotting here the x component of the velocity, and you see here that the signal is of course random, okay, because I'm generating it randomly the whole method. And it somehow has a time scale that you see in here that is similar, a sort of wavelength, which is related to the time scale, okay, that we are able to see as well in this power spectral density that, as you see, is narrow banded, okay, which makes sense because this is what we are imposing actually in our method. Here we have the very same simulation, but represented in 3 dimensions again. Okay, we have our cylinder, we have our perturbations, we are plotting in here the Q criterion contours. Okay, and we have the colors. The colors refer to our zeta component of the vorticity. Okay. Again, it's the same simulation, but with a different representation. Okay. So once I've shown you just some of the results and the method that I've been performing for the free turbulent perturbations, I'm just gonna give a little introduction on uncertainty quantification and why we do this. Okay, typically, when we want to address our problem with uncertainty quantification, we usually have some stochastic inputs, okay, and we want to know what happens in some responses that we are interested, okay. For that, we usually have an uncertainty quantification framework in which we usually have a simulation code, or which is a black box, usually because we are not actually interested of what is inside, but also in the response of the system, okay. I'm just gonna explain a very simple example of how we would apply this to a one-dimensional case, okay? Imagine that we have a pitching airfoil with mean pitching equal to 0, okay? Which is basically oscillating in pitching from, let's say, from minus, it doesn't really matter, but it's oscillating in pitching with mean pitching equal to 0, okay? And we want to perform an uncertainty quantification analysis varying the mean pitching from -4 to 4, okay? And with this, we want to see the effect on the, for example, the mean lift over, for example, 2 periods, okay? So what the first thing we could try is to, or could be to generate a normal distribution of mean pitchings, okay, with a given standard deviation according to this variation. In this case, I'm using 2 sigma equal to 4, okay, and a mean which would be the same as the nominal case. In this case, 0, okay. What we would do, firstly, a thing that maybe makes sense to do is try to do a Monte Carlo directly on our simulation code. Okay, the thing is that this is completely unfeasible because our simulation code is expensive. Okay, it's computationally expensive, so this is unfeasible, very expensive. Then it seems like a good idea to build a surrogate model that in the end is an analytical function, okay, of n dimensions. In this case, it would be of 1 dimension because we are in 1D problem, okay, which is very cheap for us to evaluate, okay. And the thing is how we do this, okay. And then we build, since we want to vary our mean pitch between -4 and 4, we are going to build a sparse grid in this interval, okay, basically a 1D grid with a rule, okay, for the points. Then we're going to simulate these points of the grid to get with our simulation code to get our mean lift coefficient as a function of this alpha m, okay, the mean flow, the mean pitching. And then once we have our data, the whole data in X and Y in this case, which will be alpha and CL, we build our surrogate model using uncertainty quantification techniques, as could be stochastic allocation or polynomial chaos expansion. Okay, this is in the end a sort of interpolation. I mean, depends on the method. Okay, can be projection, can be least square, can be in the end. Both these of these two methods have their own theory behind them. Once we have our surrogate model, we perform the Monte Carlo. Instead of use on our simulation code, we are going to perform our Monte Carlo on our surrogate model so that we get an approximation of our CL of alpha m. Okay, because this is very cheap now to evaluate because this is a non-analytical function. And then we get statistics, we get our probability density functions and of the CL, of the mean CL, and so on. Finally, what is usually done in this kind of problems is to increase the points in the grid until we reach convergence in our statistics. Okay. So in this slide, what I have is mainly what I've just told you. Okay, but for a general case, so I think I'm not gonna enter into the detail. It's just exactly the same, but for a general case, not for the airfoil pitching. Okay. And finally, I'm introducing in here a tool that we are using that is this LU-DVM, less modulated and steady discrete vortex method, which is basically a code that solves the 2-dimensional unsteady airfoil flow problems with unsteady thin airfoil theory and improve with intermittent leading edge vortex model. Okay, so we like this for uncertainty quantification because this is actually a low computational or has low computational cost. Okay, so the simulations are actually very cheap to run and provide very reasonable results. Obviously, they are 2-dimensional, okay, and they are based on potential flow. But since they are improved with this leading edge vortex model, they somehow are able to reproduce kinematics, as you see here. You have here an example of a simulation of a NACA 012 airfoil in pitching and heavy motion using this method, and as you see, it is able to reproduce the wake of the kinematics and so on very nicely. In fact, we performed a study. Actually, it was performed and directed by me and Oscar Flores by Juan Francisco Molina in his bachelor thesis, where we perform an analysis of a pitching and heaving airfoil using this tool, this discrete vortex method tool, okay? And also we compare it with the experiments performing here in the water tunnel of UC3M by Raiola, is gathered in the paper of Mauricio Raiola 2020, okay? What we did, but basically what in this case he did was performing like 6 one-dimensional analysis of uncertainty quantification for different parameters, okay? In the end, the pitching and heaving airfoil kinematics are defined by several parameters, okay? The one I showed you before was the mean pitching, but we also have the pitching amplitude, the phase between the pitching and heaving, the pivoting point of the airfoil, the heaving amplitude, and the reduced frequency of the motion, okay? And every single of these variables were analyzed or were varied into a range that was of interest for the experiment, okay? As you see in this table. In the end, after performing the six analysis, we end up reaching a CL versus time curve, okay, with percentiles, okay. Basically, with this analysis, we were able to compute the 95 and 5 percentiles, which are those curves, okay, and also the median, okay, which is in yellow, and we were able to get the experimental results inside those percentiles, which represent actually a very good fit in this case, because it's telling in the end that makes sense what has result. Of course, these percentiles are computed based on this code, okay, and this is not DNS, sorry, but actually it represents a very good fit. And well, I think this is all from my side, at least for uncertainty quantification. Just finally, I have a slide telling just a little bit of what I'm just doing right now. I'm validating the ST autocorrelations of the free stream perturbations. I'm implementing strategies to decrease the computational cost of the method, such as stepping with piecewise linear interpolation. We are working to apply this to real external aerodynamics problems. In the end, what I've shown you with the cylinder is more is small case. It's more a toy problem than a real application. It has a very low Reynolds number. The grid is a little bit coarse still, and so on. And finally, I'm well, not only me, but almost the whole group is familiarizing with Dakota tool as a framework for uncertainty quantification, and we are trying to couple this Dakota tool, which is a tool of Sandia National Laboratories, with our in-house codes. So this would be all from my side.